This UCSD TV program is presented by University of California Television. Like what you learn? Help others discover UCTV podcasts by leaving a comment or rating for us in iTunes.
As many of you know, I'm Nigella Hilgarth, and I'm the Executive Director of the Birch Aquarium. And this is part of our Perspectives on Ocean Science lectures, the Jeffrey B. Graham lectures. But this is a very special lecture because it's the 4th annual Charles David Keeling Memorial Lecture. And you can tell it's a special lecture because we had artichoke dip to eat and other exciting things. But joking apart, I'd be looking forward to this evening very much. And we're very lucky to have with us tonight Professor Ralph Keeling, who is Charles David Keeling's son, and he is going to introduce our wonderful speaker tonight, Richard Somerville. So thank you.
So thank you, Nigella, and thank you all for coming. As she said, this continues with the 4th annual Charles David Keeling Lecture. That is strange for me to say his name because he is my father. But he had a legacy of CO2 measurements showing that carbon dioxide was rising, putting global warming on the research agenda, and changing the way we think about the world. And I think that legacy will evolve with time as new developments happen. I don't think we know exactly where this lecture series is going to go in the future, but events like Hurricane Sandy remind us that we're in uncharted territory. The selection of the speaker this year went without geographic prejudice to my close colleague Richard Somerville, a very distinguished colleague within our ranks here at the Scripps Institution of Oceanography. He has expertise in theoretical meteorology and in computer simulations of the climate system. As background, he was an undergraduate at Penn State University, where he received a BS in meteorology and went on to get a PhD in meteorology at New York University. He's been on the faculty here at Scripps since 1979. His current title is Distinguished Professor Emeritus and Research Professor. He's received numerous awards. He's received awards from the Meteorological Society both for his research and for a popular book he wrote on climate change called The Forgiving Air, Understanding Environmental Change. And a new edition of that book was just published a few years ago in 2008. Among his honors, he's also a fellow of the American Association for the Advancement of Science and the American Meteorological Society. And I would particularly emphasize a recent accomplishment of his, which was being a coordinating lead author of the 2007 Fourth Assessment Report of the Intergovernmental Panel on Climate Change. This was the report that received the Nobel Prize. Richard played a very large role in that. Being a coordinated lead author meant that he was carrying a lot of weight and a lot of headaches around for a long time. So it's really a very important and significant accomplishment that really defines our understanding. And it's partly based on that expertise and his broad understanding of the science that he has important messages for us. So thank you, Richard, and thank you.
Well, thank you, Ralph, for the kind introduction, and thanks to Ralph and his mother, Louise Keeling, and the group for having invited me to give this talk, and thanks also to Nigella Hilgarth and Cheryl Peach and their colleagues at the Birch Aquarium for making this all happen, and special thanks to you all for coming. I knew Charles David Keeling, known to everyone as Dave, for about the last 25 years of his life, And he had a very original mind. He was an interesting person as well as a great scientist. And I'm going to take time to tell you a couple of little stories. Dave Keeling wrote a fascinating autobiography about the rewards and penalties from measuring the Earth. And he wove in some of his personal history. He said that I'm quoting now, during the Great Depression, my father, although personally successful, became distressed about the economic future of our nation. And in the late 1930s, he quit his work in order to study, teach, and preach banking reform, thereby plunging our family into the poverty he was distressed about. Dave had a winning way with words. He went on to say, I was exposed so extensively to my father's ideas in economics and banking that I abandoned a curriculum in chemistry at the University of Illinois simply to avoid taking a required course in economics. I felt quite passionately that my exposure to economics at home had been enough. Dave Keeling did do a PhD in chemistry at Northwestern and a postdoctoral fellowship at Caltech, and that's where he began measuring atmospheric carbon dioxide using an instrument of his own design. And he made tests and learned a lot as a postdoc. He went outdoors to a state park in Northern California to find unpolluted air, not available in Pasadena. And he wrote, not being sure that the CO2, even in pristine air next to the Pacific Ocean, would be constant, I decided to take air samples every few hours over a full day and night. Why did I devise such an elaborate sampling strategy when my experiment didn't really require it? The reason was simply that I was having fun. I liked designing and assembling equipment. And at the age of 27, he wrote the prospect of spending a lot more time at Big Sur State Park didn't seem objectionable at all. Dave Keeling was encouraged by Harry Wexler, in charge of research at the Weather Bureau, and by Roger Revelle, who was then director of Scripps. And he moved to Scripps in 1956 and stayed here for the rest of his career. And the famous Mauna Loa CO2 record began in 1958. This is a rather characteristic pose of Dave Keeling in front of Scripps pier. And now I want to say a little bit about the CO2 record, which is so central. It's something that's always present either tacitly or explicitly in every discussion about man-made climate change. This slide here shows on the right the observatory in Mauna Loa. This was intended to be part of the International Geophysical Year, an 18-month period. And at the lower left, you see the first decade and a half or so of Keeling's measurements, which began in 1958. And what you're looking at is the amount of carbon dioxide in the atmosphere. Concentration is the jargon term, and it's expressed in parts per million by volume, which is equivalent to the number of molecules per million molecules. So it's a rare gas. The atmosphere is almost all nitrogen and oxygen. But you see here that out of 1 million molecules of air in 1958, about 314 of them would be carbon dioxide molecules. And you see the graph there at the lower left tracing the first few years. So you can see a lot of things on this graph just right away. First of all, it's increasing with time. So Keeling was the first to measure atmospheric carbon dioxide concentration accurately, and he was the first to discover that it was increasing in the atmosphere. There were previous attempts at measurement, but none of them had the accuracy that he had. He also discovered this annual oscillation, and that's due to plants photosynthesizing in the spring and drawing down the carbon dioxide in the atmosphere and converting it to plant material. And then in the fall, or at the cold part of the year, the leaves fall off, the plants respire, CO2 is returned to the atmosphere. He discovered all these things, and he also discovered that the rise in carbon dioxide was due to human activities, and in particular to burning fossil fuels. So we owe him all that, and that was apparent early on in the early 1960s, but he continued these measurements, often with great struggles to find appropriate funding. And here's what the Keeling curve, which is the popular name for this, looks like today, or actually looked like in December, which was the last time I downloaded it. It's being frequently updated. And you can see that what was 314 then is now 395 or so, pushing 400 today. That's a remarkable story right there, because that increase is something like 25%. Keeling's measurements were very accurate. He said that he built the instrument to a greater accuracy than he thought it needed to be, just because he figured out how. And the rate of increase has been going up. You can even see by eye that the upward slope of the curve in the early years is less strong than the slope in recent years. So Keeling made the discovery, we owe it entirely to him, that mankind is changing the chemical composition of the atmosphere in important ways. And the greenhouse effect had been understood for a long time. The fact that carbon dioxide and other molecules trap infrared energy, they trap heat essentially, had been known to experimental physicists in the middle 1800s. John Tyndall in London put carbon dioxide in a tube and measured how it could absorb infrared energy, which he could shine on it. And the first attempts to understand the implications of this for climate date back to the 1890s. So in a sense, the science was there connecting carbon dioxide amounts in the atmosphere to climate change until we had the measurement showing that the CO2 was actually increasing, and increasing much more quickly than had been foreseen in the 19th century. There were more people using more coal and oil and natural gas, and the rapidity of the growth of CO2 was a surprise to everyone. But it was Dave Keeling's measurements who showed this unambiguously. And these measurements are being continued today by his son Ralph and by others elsewhere. And they are the bedrock data, observational data, on which our understanding of man-made climate change rests. I have one more little Keeling story to show you. This is the Great Hall of the National Academy of Sciences in Washington. Election to that was one of Dave's many, many honors. And here's the Keeling curve, at least as it was in about 2002, up there with some of the iconic achievements of modern science, such as Darwin's finches or the double helix of DNA. So the world now recognizes the importance of the work that he did. Okay, I'm going to show you some more data now. This is the temperature, average temperature of the surface of the Earth from 1850 on the left to 2010 on the right. And there's several things that can be said about this. You're looking at compilations of this data by two centers. The purple one is in England, the blue one is in the United States. The dots connected by straight lines are the yearly numbers, the annual average temperature of the surface of the Earth, the atmosphere near the surface, averaged over a year. And these purple and blue curves are the smooth connection, smoothing out the interannual wiggles, which are largely due to natural fluctuations, including especially El Nino and La Nina, and also volcanism, for example. It must be said that in the 1800s, on the left side of the curve, the data was not as good as today. There weren't as many temperatures, there weren't many thermometers, they weren't as calibrated together as well, there weren't any satellites, and so on. As time goes on, these errors get smaller and smaller. In recent years, as you can see, the compilations fall essentially on top of one another, and there are several centers in addition to these two that keep track of this. The data all agree they've been carefully quality controlled, and sensible assumptions have been made about missing data or poorly cited data and so on. So that we know now that the world is unambiguously warming. It looks like it was warming also in the early part of the 20th century, and then there's a period from roughly 1940 into the late 1970s where the temperature cooled slightly, didn't change much. It's still a bit of a mystery. We're not sure about that. The most popular and probable explanation is that in this period here, there was more pollution in the air. The Clean Air Act in the US and comparable laws in other countries hadn't been passed, and so that the pollution particles in part reflected away sunlight and temporarily masked the warming due to the increasing amounts of carbon dioxide. There's a very rapid warming since then, at about 0.2 of a degree Celsius per decade, or 1/3 of a degree Fahrenheit per decade, and it's continuing today. And there's very little doubt that it's human caused, and I can talk later about the reasons that we know this, but essentially the alternative explanations can be ruled out quantitatively. We know what causes ice ages to come and go. For example, it's changes in the Earth's orbit around the sun, which affect how sunlight is distributed with seasons and with geography, and that's just too weak and too slow to be responsible for something happening this quickly, a few decades. That works on timescales of thousands and tens of thousands of years. Similarly, we can measure the amount of radiation that the sun emits, and that changes very slightly too, about 0.1% over the 11-year solar cycle. And when you convert that into the same numbers, it just doesn't compare with the effects of CO2. Also, when we measure how the warming is distributed with space and with altitude in the atmosphere, it doesn't fit other possible mechanisms. So a lot of good, clean scientific detective work. There's a whole topic in climate science called detection and attribution, to detect unnatural climate fluctuations and then to attribute them to specific causes. And there's very little doubt in the expert community now that the bulk of the warming observed in recent decades is with high probability due to human activities. That's something that's accepted by mainstream climate science. Besides temperatures, there are lots of other things we can point to. You know, there is, as you may know, a dark side, a disinformation campaign, very bad but well-funded and clever people who would like you to believe that modern climate science is controversial and not well-funded and hangs from some slender thread of evidence so that if a particular data point is shown to be mistaken, or then the whole edifice collapses like a house of cards. But in fact, there's not a slender thread. There's a big, thick rope woven of many chains of evidence. And here are 10 indicators that the climate is warming. Some of them are obvious. We've talked about temperature over land and temperature over the oceans. The oceans is warming. The sea surface temperature is warming. The great majority of the heat that's been absorbed in the climate system in recent decades is in the ocean. Something like 90% of it is in the ocean. Sea level is rising. White arrows here mean the measurement is going up. Black arrows mean it's going down. Sea level is rising for several reasons. One is that the ocean expands thermally, like many things. It takes up more volume as it gets warmer. But another is that ice on land melts and the liquid water eventually flows into the sea. We know also that sea level is rising now because Greenland and Antarctica are losing mass. Their ice sheets are contributing to sea level rise. Glaciers are in retreat worldwide. Snow cover is retreating. I'm going to talk more about sea ice in a moment. Water vapor is more plentiful in the atmosphere. The atmosphere today has more water vapor in it than it did, say, 30 years ago. That's not a conjecture. We can measure that. But it's also expected because a warm air holds more water vapor, so to speak, than cold air. Or for you physicists here, the saturation vapor pressure is a strong monotonic increasing function of temperature. So there is more water vapor, and that has many ramifications. Most of the kinetic energy, the energy of motion of the atmosphere, can be traced to its source in phase changes of water between liquid, gas, and solid. And the water also contributes to more rainfall. The rainfall is falling more often in heavy deluges than in drizzles, you might say. And it has implications for the strengths of tropical cyclones, which I'm going to come to in a bit. So there are many, many independent measurements that let us conclude with essentially no uncertainty. Unequivocal was the IPCC's phrase, that we're living in a warming world. I want to say something about sea ice, I just promised you. And what you're seeing here is the average sea ice at the September minimum. Arctic sea ice, we're in the Arctic here, is a minimum in September. The summer melt season is ending, the winter ice forming season is just beginning. So if you look around the year at the time when the sea ice extent, the aerial extent of ice in the Arctic is least at September. And this yellow period here shows this period of 17 or 18 years, starting with the beginning of the satellite era. We couldn't observe this well from space before 1979. We see the average extent. In 2007, there was a striking reduction in the sea ice extent that had been unforecast. And 2007 happens to be the year that the most recent IPCC report came out. IPCC, the Intergovernmental Panel for Climate Change, and agency under UN auspices, which organizes scientists to write these 1,000-page summaries of the state of climate science, produces one of these reports every 6 years or so. There's one in progress now. It'll come out starting in this September. And this report came out in February of 2007. In September, the forecast of how sea ice would be reduced was shown to be wrong. It was much less. And it continues to be reduced year after year. And now the all-time low extent of Arctic sea ice occurred this past September. And I've got a movie here, which if it works, will show that. So you can watch the sea ice in kind of time lapse going from 1979 to the present. So here are the years 1980s. You can see it's different every year. It's not the same. It depends on winds and currents and lots of other things. And in the 1990s, it still looks about that. But now we're about to enter the current century. Here's 2000. And watch 2007. It's suddenly very small. And now watch 2012. It's smaller still. And if you look at this numerically, it's quite striking. I've got a graph here to show you. These graphs are all from the IPCC report last time, 2007, a report written by a number of scientists in 2009 called the Copenhagen Diagnosis to brief the UN climate negotiators, and a new national climate assessment now out in draft form for comment being produced by the US government. I'm a co-author of all of those things, so I'm not entirely out of bounds in showing you them. But so here is the Arctic sea ice in 2012 compared to what it was in two representative earlier years. You can see that it's far less. And if you graph the amount, starting in 1979 when satellite measurements began, if you graph the amount here, you're looking at millions of square miles here. This is 3 million square miles or so at the beginning part of the record. This is the 2007 surprise minimum amount. And this is the 2012 minimum amount, less than 1.5. So the extent of the area covered by sea ice in the Arctic has dramatically been reduced by about a factor of 2. That's about 50%, if you like. It was 3 in round numbers here and 1.5 now. Now, mind you, at the same time, the thickness of the ice has also been diminishing. The ice in the Arctic now is thinner than it used to be, thus more vulnerable to melting. But the volume of the ice, essentially the product of the thickness and the areal extent, shown here, is thus being reduced more rapidly than the areal extent altogether. So the ice is in fact disappearing. There are various estimates about when it will be all gone. The comment that I like best comes from the US Navy, which has said, we will have one more ocean to patrol. And so many, many consequences flow from that, of course. Shipping, danger of oil spills, extraction of minerals there, national boundary controversies, and so on. But there's an example where the climate is changing more rapidly and more severely than had been foreseen by any model. And in defense of the scientists, this isn't easy to model or to forecast. It's not just a question of the ice melts when the sea gets colder than 32 Fahrenheit, because it's a question of when do the winds and the ocean currents move the ice to parts of the Arctic that are more vulnerable to melting. Here's another variable in the climate system that has been changing more rapidly than had been foreseen. What you're looking at here is sea level. The global average sea level changes in centimeter. 2.5 centimeters is an inch. And shown from 1970 on the left to near the present on the right, the red line here are sea level measurements from tide gauges. Tide gauges are essentially floats in tubes at shorelines. There's one at the Scripps Pier just down the hill from here. And then here are satellite observations. The tide gauges have been supplanted in large measure by satellite altimetry. Instruments can measure the distance from the satellite to the ocean, and that gives you global coverage too. You can see that where the two are shown here, they lie on top of one another. And what you may be able to see is that there's a gray area here called IPCC predictions, and the sea level is rising near the top of that range. So sea level is running near the worst case. This is a graph updated to 2010 from a paper published in Science in 2007 that I was a co-author on, and we concluded that comparing the predictions of earlier IPCC reports, the fourth one just came out in 2007, there were 3 before that over the preceding 20 years or so. It must be said that the IPCC assessments have not exaggerated climate change, and in some cases, such as sea level, seem to have underestimated it. We don't know yet what the new IPCC report will say, although it's been out in draft form for review comments, but I'm confident that it will have a higher upper limit on what sea level might be. And many projections have ranged up to 2 meters, roughly 6 feet, by 2100, a very serious level. This is global average. Sea level at a location can be more or less because the land can be rising or falling. But it must be said also that this is an area where there's a lot of research that still needs to be done, and there's more than one way to model sea level rise, and different kinds of models, different scientific approaches don't yet converge. And so this is an area of active research, and we don't know, but we can't rule out sea level rise in excess of 3 or 4 feet, whereas the IPCC report predicted up to 2 feet in the last report that came out. Now, on this graph is temperature and carbon dioxide, and let's look at the black line first. That's carbon dioxide, 1880 on the left, the present on the right. So starting in 1958, these are Keeling's measurements, smoothed out to remove that annual modulation I talked about. So where do these data come from when Keeling wasn't busy doing this? And the answer is that's a remarkable story. That's a story that's a reflection of some very clever scientific detective work and some amazing good luck. And the good luck is that there are 2 places on Earth where air from previous times, reaching back into the geological history, is available today. And that's Greenland and Antarctica. And it's present in the ice. When ice forms in Greenland and Antarctica, the ice forms because the weight of new snowfall compresses the snow under it from previous years and eventually turns it to ice, and trapped in the ice are tiny bubbles of air, if you like, fossil air preserved from that time. And the technology now is so good that we can go to Greenland and Antarctica, drill, bring up cores of ice, date it, take the ice to the laboratory, and measure the amount of carbon dioxide in these tiny bubbles. And so we know that it was rising gradually before Keeling's measurements began, and that in the times before the 1800s, when human activities presumably had no strong effect on climate, it was near a value of 280 in these same units of molecules per million molecules. So CO2 has been rising, and the lines here are, each bar is 1 year, is the average surface temperature, the same measurements you saw earlier. And you can see there's a lot of variability. The average temperature, this is in Fahrenheit degrees, so the average temperature over this period was about 57.6 Fahrenheit globally, surface temperature, day and night, summer and winter. But in all the years before the 1930s, you might say, every year was below that average, and in recent years, every year's been above it. And in between, the period I mentioned, 1940 to 1970, when there wasn't much change, maybe a slight cooling on the whole, there were both above average and below average years. Again, the natural variability is due to factors like El Nino and the occasional strong volcano, which temporarily cools the climate for a year or two. And so these things here are some of the strongest El Ninos on record. But that there's a warming now and that this period is different from this period isn't any doubt at all. This is that same temperature variation now shown as maps from here you are in the early 1900s till today. Blue is cooler than average, and yellow and orange are warmer than average. And you can see here it's still some blue areas and so on, but starting in the 1970s, you start to see the yellow and orange colors predominating. And by the time this ends, at 2010 or so, you can see what the world looks like today in this picture. There's warming everywhere. There's more warming over the continents than over the oceans. There's more warming in the north than in the south. And there's the strongest warming in the Arctic. This is a Mercator projection, so it exaggerates the area of the Arctic, but the warming is strongest in high northern latitudes. And that's because of a number of feedbacks that we think we understand, of which the most important is that when warming occurs in the far north, the ice and snow melt, as we've seen, and the ice and snow having melted reveal darker water and darker land that was under them, which reflect less sunlight and therefore absorb more sunlight. So the chain of events is carbon dioxide causes the warming melts snow and ice. The melted snow and ice make the surface darker. The darker surface absorbs more sunlight, and that adds to the warming. It's a vicious circle, as though you had your house wired funny, and when it got hot, it turned on the furnace instead of the air conditioner. If you want to take home one slide from what I have to say, I highly recommend this slide, and I'd like to walk you through it. What's shown here as a function of time from 2005 on the left to mid-century on the right is the rate at which we're emitting carbon dioxide, gigatons, which is geek speak for billions of metric tons of carbon dioxide, which is a lot. You see, we're putting upwards of 30 billion tons of carbon dioxide into the atmosphere, again, mainly from burning coal and oil and natural gas, but secondarily from deforestation, cement manufacture, and another another number of sources. And you can see that it's been going up in recent years. In fact, it's been going up continually for many years. There was a kind of one-year blip due to the Great Recession, but it's resumed going up again, driven now largely by rapid industrialization in developing countries with large populations, such as India and China, that are exploiting coal energetically. The three curves here represent three possible scenarios. This was from the Copenhagen diagnosis, which came out at the end of 2009. And so the dates here are chosen so that we could say, if you pick 2011 as the year when you would turn things around and mankind would stop raising its emissions every year and start reducing them, then this green line here is a scenario in which the emissions are reduced gradually so that by mid-century they haven't gone to zero. The blue curve is one in which emissions keep growing for another 4 years and then start being reduced and reach zero before mid-century. And the red curve is one in which emissions continue growing throughout the present decade and then decrease very rapidly, reaching zero by 2040. And what these three curves have in common is that the area under them is about the same. And it's the area under them that represents the total cumulative emissions of carbon dioxide during this period. And because carbon dioxide lasts in the atmosphere a long time, it's proportional to the total amount of CO2 in the atmosphere. And the amount of carbon dioxide in the atmosphere is what matters to the climate. Climate just reacts to how many of what kinds of heat-trapping gases are there. The more there are of an important gas like CO2, which is by far the most important man-made gas, the warmer it gets. So what these curves have in common is that the area under them represents the amount of CO2 such that you'd have a 2 out of 3 chance of limiting global warming to 2 degrees Celsius, which is 3.6 Fahrenheit, above what it was in the 1800s. This is done in response to what some governments have decided. The European Union, for example, which is Western Europe, which has more people and a larger GDP than the United States, has formally decided as an official policy position that it will try to limit global warming to 2 degrees Celsius, or 3.6 Fahrenheit in our units. Why? It's a judgment call. It's not a scientific decision. It's a little bit like your cholesterol, you know, that your doctor can't assure you that if your cholesterol is below a certain number, you can't have a heart attack. And if it's above that number, you're sure to have a heart attack. It's just that the risk goes up. And so this is a measure, you might say, of how much risk you're willing to accept. And it's also a measure of economic priorities and a number of other things. But the European Union, after careful consideration, has said 2 degrees Celsius is a target that they'd like to strive for. And a number of other countries have signed on to this informally as an aspirational goal. Some countries, especially low-lying island states, have said we'd like to have less than that much warming. But if you want to have that much warming, if you, the governments of the world, take that decision, then the science can help you say what it would take to get it. And what it says is there's a certain amount of CO2 that you can have in the atmosphere and no more. We don't know exactly, that's why this is a 2 out of 3 chance, but it says that if that's your goal, it's better to start reducing emissions right away, because then you can glide down with reductions of 3 or 4% per year. If you wait until 2015 before you reduce them, then to meet this goal, you have to decrease them by about 5% per year. And if you are going to procrastinate and dither, as the world has done, until 2020, then you must reduce them by this rate here, which economists will tell you is essentially difficult or impossible to do. I didn't draw this graph. It came from a number of German scientists, but I named it. I called it the ski slope diagram. This is the bunny slope here, and this is the intermediate ski slope, and this red line is the double black diamond expert slope. So that's where the urgency in my title comes from. It says this is not an issue like steel tariffs, you might say, or trade agreements that you can think about getting it done next decade if you can't get it done this decade. This is something that Mother Nature puts a time limit on. There's only so much CO2 you can tolerate in the atmosphere, and in this range, the climate change is just proportional to that amount of CO2. So that if you're serious about a target like 2 degrees warming, this is what you're faced with. You can't think about decreasing things in 50 or 100 years. You have to do it in 5 or 10 years. And that's the urgency. And it's in that sense that this urgency has nothing to do with politics or ideology. It's just science saying in a straightforward way that the physics and biogeochemistry of the climate system say that it's urgent to do that. It has to start happening in a few years. Alternatively, if you don't do anything, then you're not going to make that target. And you're going to have to cope with more climate change. It's been said that we're either going to mitigate climate change, that is, do this kind of thing to reduce it, or we're going to adapt to the changed climate, or we're going to suffer. And what we get to choose is how much of mitigating and adapting and suffering we get to do. So that's the take-home message of what I have to say. But not the last slide. You know, these temperature numbers are a little bit like a fever in your health. A higher fever is a more severe disease, but they don't tell you what all the aspects of climate that matter to people and to ecosystems are, because it's a lot more than just temperature. It has to do with droughts and heat waves and sea level rises and threats of stronger hurricanes. And I want to say a bit about those things now. So what you're looking at here is two maps of the world, two future scenarios. The one on the left, a low pathway, something like the bunny slope on the previous diagram. And the one on the right, a high pathway, essentially business as usual. And it illustrates that the fact of the matter is that the future climate, the one that our children and grandchildren will deal with, is in our hands. We get to choose, and we will saddle them with this if we continue increasing in population, increasing in prosperity, increasing energy use, energy primarily generated by fossil fuel use, which is upwards of 80% of global energy use today. And this is the opposite. This says take steps to switch away from fossil fuels and to do all the other things you can do to reduce the amount of carbon dioxide going in. You can see the scale down here. These dark reds have to do with temperature rises in Fahrenheit of 9 to 15 degrees, whereas these yellow and orange has to do with 3 to 5 or 7 degrees at most. So it's a very different world. This is the same kind of chart for the United States, and you're looking here. Keep in mind that the US average temperature has already increased by 1.5 degrees Fahrenheit since 1895, and more than 80% of that has been in the 32 years since 1980. So this says that by 2100, on high emissions, you can expect 5 to 10 degree increases in much of the country, more in northern Alaska for the reasons I mentioned, whereas on low emissions, you can restrict that. And I think now what I'd like to do is to talk a little bit about one particularly dramatic kind of consequence of climate change, which is changes in extreme weather. There's no doubt that the changes I've described express themselves often through changes in extreme weather. So that we know, for example, in the US right now, that the number of new high temperature records being broken every year far exceeds the number of new low temperature records being broken. If the climate weren't changing, you'd expect just by random chance there'd be about as many new highs as new lows, but we're breaking more highs. We're also seeing more rain falling in deluges, in gully washers, you might say, than in drizzles or light rain events. And we're beginning to see changes in heat waves. We're beginning to see changes in droughts. Happened last year in this country. The heat wave in 2010 in Russia was an example. The heat wave in 2003 in Western Europe that killed 35,000 people, and chiefly in France, is likely to have been exacerbated by climate change. You have to keep in mind that weather today is taking place in an environment, on a stage you might say, that has been altered by climate change. Temperatures are higher, sea surface temperatures are up, water vapor content of the atmosphere is up, and so on. I'm going to say a bit more about that, but first I wanted to show you a film of Hurricane Sandy from last fall. This is a satellite loop, and while it's playing, you can see Hurricane Sandy at the lower right forming in the Caribbean. I'll remind you of a few facts about this storm. It was a late season, late October, post-tropical cyclone. It swept through the Caribbean and up the east coast of the United States in October of 2012. It left many dead, thousands homeless, millions without power. The total damage, and according to most recent estimates, is at least $75 billion with a B. It's the second costliest Atlantic hurricane behind only Hurricane Katrina, which hit New Orleans in 2005. The death toll from Sandy was at least 285. It famously was a hybrid storm. This tropical cyclone moved into the extratropics and merged with this mid-latitude cyclonic weather system to create a hybrid storm, something that we're only just beginning to study and understand. Sandy made landfall in the US on October 29th. Up here are the dates. 2012 is the year, 10 is October, 26 is the date. On October 29th, near Atlantic City, New Jersey, with winds of 80 miles per hour. Through bad luck, a full moon made high tides about 20% higher than normal and amplified the storm surge. That is, the ocean water brought ashore by the storm. It was also amplified by the rising sea level. As you may recall, seawater surged over lower Manhattan seawalls and highways and into streets. The water inundated tunnels, subway stations, and the electrical system that powers Wall Street. The hurricane force winds of at least 74 miles an hour at this landfall point extended up to 175 miles in radius, and tropical storm force winds extended out to 485 miles in radius. So Sandy at its peak covered the northeastern part of the United States, affected 24 out of the 48 states, and was essentially 1,000 miles across at about this point here. Sandy's strength and angle of approach combined to produce a record storm surge of water into New York City. In Battery Park, that's the lower tip of Manhattan, the storm surge topped 13.9 feet, surpassing the previous record of 10 feet in Hurricane Donna in 1960. And the surf reached a record level in New York Harbor when a buoy measured a 32.5-foot wave, which was also taller than the tallest, far taller than the tallest wave seen up till then. I'm going to show you a little bit to remind you of Sandy's damage, but this is an extraordinary satellite loop. And I thought before I showed you the damage, I wanted to say a little bit, because I don't want to close without mentioning a number of popular myths, things that are widely repeated and aren't true, that are part of the disinformation campaign that is attempting to create confusion among politicians and people in the media as to what climate science can and cannot do. So here's a popular myth. What you're looking at here is the average temperature of the world from 1970 till 2010. And there's been a warming here. As you can see, this is in Fahrenheit degrees. So there's been a warming of, since this is 0, and it starts above 1, of roughly 1/3 of a degree Fahrenheit per decade, or about a degree and 1/3 over 4 decades, shown by this red line. When you hear people say global warming has stopped since 1998, or global warming doesn't happen anymore, what they're invariably doing is cherry-picking these data so that if you pick 5-year periods, you can get either slightly falling, sharply rising, sharply falling, sharply rising. And here's 1998, a strong El Nino. And so you can say, well, in this period here, the temperature has leveled off, although in these last 2 years, it's higher than 1998. El Ninos bring heat out of the ocean temporarily and put it in the atmosphere. So El Ninos are spikes and La Ninas are these troughs. But the real fact is that you need a couple of decades, 17 years or more, to create a meaningful long-term trend for this particular variable of global average temperature. And short trends don't mean anything, and they're dominated by this natural variability, El Ninos, volcanoes, and so on. Whereas the long-term trend is quite unambiguous, and if you look at the same data a different way, you can bin it in decades and say that the 1980s were the warmest decade on record at the time, warmer than anything before. But the 1990s were even warmer, and every year in the 1990s was above the average for the 1980s, and every year in the 2000s was warmer than the 1990s average. So the fact that the world is warming is quite unambiguous, and it's laughable to say that it has stopped or paused or is no longer discernible or anything else, masked. It's just warming, that's just a fact. So it's just a good example of how to lie with statistics. And at the end, I'll give you a website that refutes a number of these myths. I've never met anybody who says that they believe them, but they always have somebody named Uncle Joe who comes to the party and spouts this nonsense, and they want to know how to refute Uncle Joe. So I'm going to give you the quick Cliff Notes crib sheet for that. I'm going to leave the screen dark for a second while I say something about the question of, did global warming cause Hurricane Sandy, which I'm asked about twice a day, every day. And the best answer that we know is to say courteously, that's the wrong question. because the metaphor we like to use is that carbon dioxide is the steroids of the climate system. You don't see its effect in one weather event, you see it in the statistics. When the baseball slugger was clean, he still hit home runs. So when you go to the ballpark later after he's been on steroids and he hits a home run, you can't say whether that home run was due to the steroids. He was a powerful major league slugger before. But what you can see is at the end of the season in the statistics, his batting average has gone up, his home run productivity has gone up, his slugging percentage has gone up. And climate is the statistics of weather. So just as Hurricane Sandy is operating in an environment that's been altered by climate change in such a way that we expect stronger hurricanes, and we see statistically greater instances of strongest hurricanes in the North Atlantic basin where we have the most data, but in the rest of the world where almost all the hurricanes are, we don't have the data to show it yet. There's a lot of year-to-year variability, but we still can say that on average we would expect to see the odds change in favor of stronger storms. So it's tricky, and you can't say that climate change did or did not cause a particular event, but you see it in the statistics of the ball player, and the statistics of weather is climate. Okay, I wanted to, in closing, say some optimistic things, but I did want to make the point that extreme weather is an aspect of climate. This is an example of things that might be done, and if you go through this list here, it's a familiar list. The low-hanging fruit is energy efficiency and energy conservation. That often comes at small or even negative costs, but there are many things that can be done, and I'm not going to go through them all. It's a list that I think you know, but all the careful analyses show that taken together they can do a lot. There's no single silver bullet, but there's a lot of silver buckshot. And so there's a lot of different things you can do, and these wedges in the jargon of the trade are examples of them. So it's possible to do it. It's really a question of political will. The technology is there, and there are already good examples of countries and US states that have vastly increased their electricity generation from renewables, for example. We know that it's possible to vastly improve vehicle fuel mileage and so on. But the message to take home here, again, is that this is urgent. People have to raise this to a higher profile. Everybody's in favor of leaving an undamaged planet to their children, but it's not number one or number two priority. It doesn't rank with healthcare and education and a strong economy. But the fact is that, as you saw, a window of opportunity is open. It's still open. It's been open for a long time. We haven't taken advantage of it, but it will close. Remember, there's a sort of decadal timescale in which the world has to do something serious about reducing global emissions in order to meet this moderate target of 3.6 Fahrenheit warming. And once that window closes, it will stay closed. This is a special moment in my life. Last year, the Dalai Lama spent a day at UCSD, and my Scripps colleague, Virabhadran Ramanathan, and I spent a morning in Rimac on the main campus in conversation with him about climate change, which he understands and takes seriously. And experts in communication and in persuasion and in the subject of how to change people's minds say we need three things. One, we need simple messages. Two, we need those simple messages repeated often. And three, we need those simple messages repeated often by a variety of trusted messengers. And I think among those trusted messengers, people like the Dalai Lama. You don't have to be a Tibetan Buddhist to understand how revered and respected this man is worldwide. And you don't have to study a lot of history to realize what people of comparable stature, think of Martin Luther King or Gandhi or Nelson Mandela, have been able to accomplish. And I think that it's very important that in future, one critical way of raising public consciousness and raising this on the politicians' priority list is to enlist the help of trusted messengers. That's almost all I wanted to say. I just wanted to say that what science has here, the role of science, I think, in this issue is to inform the public, to inform policymakers. The IPCC reports, which are just assessments of the current research literature, rendered in a way that's palatable and intelligible and relevant to policymakers, but without being policy prescriptive, are an example of that. And the urgency here, I stress, is not political. It's just that to say that if governments will decide that a moderate degree of climate change is tolerable, then the urgency isn't ideological or political. It's fact and evidence-based. It comes from science, and it's firmly based on the physics and chemistry of the climate system. I'm going to leave this last slide up during the question period. These are some of the websites that I recommend. My site at the top, for example, has a link to the entire conversation with the Dalai Lama, which is very moving. Climate Communication is a site run by my partner, Susan Hassel, with whom I've done a lot of joint work on climate outreach and messaging. She's a communication expert, and there's a lot of good links and downloads on both of our sites. Real Climate is a blog for geeks. I look at it every day. It's run by some good climate scientists, and I recommend that you trust the main postings by the people who run the site and take with a grain of salt the comments by bloggers, which vary all over the map. Skeptical Science is the site I promised you. It's run by an Australian scientist named John Cook, who has compiled many, many refutations at various educational levels, you might say, to the common myths that are the armament of the disinformation campaign, including myths like it's all due to the sun, it's natural variability, it was, there were alligators in the North Pole, and blah, blah, blah. And IPCC, that CH at the bottom is the French abbreviations for Switzerland. IPCC has an office in Geneva. That's the site where the Intergovernmental Panel for Climate Change reports are available and downloaded. They're heavy going, but we use them as textbooks for graduate students here, and I highly recommend them to you. You've been very kind. I'll take questions now. Thank you very much. And the question, if I may paraphrase what you said, was, what happened to the ozone hole? We used to hear a lot about it, and we don't hear much about it now. And that's a success story. The ozone hole was discovered in the early 1980s. It was a sudden disappearance over Antarctica of a large fraction of the ozone in the lower stratosphere in Antarctic Spring. And we found out through a lot of very good science being done rapidly, plus a nice situation where the political world, the industrial world, and the science got together. What happened was the culprits that destroyed stratospheric ozone was man-made chemicals. Chlorofluorocarbons used in refrigeration and other uses. Freon is a popular trade name. They used to be in your car air conditioner. And DuPont and the other big chemical companies that made money on freons succeeded in making ozone benign substitutes. And laws were passed. The Montreal Protocol was the first one. There were many following laws that outlawed the production of these chemicals and required ozone-safe substitutes for them. And all of that happened. There were international conferences, technology and money changed hands, different countries contributed in different ways. But as far as we know now, the ozone hole is on the way to healing. And we expect that sometime around mid-century, it will look something like what it looked before we tampered with it. So it's a great success story. And a lot of people deserve credit. Science was certainly a big part of it. And it's often held up as a paradigm for what needs to be done about global warming. I think the big difference is it was much easier to do in retrospect, that chlorofluorocarbons and related chemical compounds were a niche chemical used in refrigeration, air conditioning, certain industrial processes. Whereas now we're talking about coal and oil and natural gas, which are a monstrous global industry supplying upwards of 80% of the world's energy. It's not going to be anywhere near as easy to change that around. And the question was that I've been talking about CO2, whereas water vapor is in fact also in the atmosphere, and it's a more powerful gas. It's responsible for a stronger greenhouse effect, a stronger heat trapping effect than CO2. And how about that, and what are there important effects of agriculture, if I paraphrase you correctly, where we've put large amounts of water vapor into the air in dry areas. It is true that water vapor is more important than CO2, but water vapor is something we can't control the amount of because it depends strongly on the temperature. And as the temperature of the atmosphere goes up, the air can hold more water vapor. And in fact, we observe water vapor increasing because the CO2 has warmed the air. So in a sense, it amplifies the effects of CO2. CO2 is the thermostat. We can control that. And when we raise the temperature of the atmosphere, inadvertently, of course, by adding CO2, it makes room for more water vapor, you might say. And so the water vapor amount increases. That's theoretically understandable, and it's observed, and it's in all climate models too. What happens locally when you irrigate a lot or spray a lot of water into the air is you can change the local climate. If you go to Palm Desert on a summer's day when everybody's got their sprinklers running, the local climate is altered. But on a large scale, we're not doing much. Palm Spring is a tiny fraction of the area of the Earth, and if you put too much water vapor into the atmosphere, it simply rains out. And in fact, the atmosphere, you might say, self-controls its water vapor content depending on the temperature. So we don't have a direct handle on that, but we know that water vapor amplifies the effect of CO2, and it's measured to do that. Dr. Kennel, former director of Scripps, has said we're going to have a certain amount of warming no matter what we do. And we may hold it to 2 degrees, we may not, but even at 2 degrees, things change. And what do we know about the 2-degree world? I think we're learning about the 2-degree world. But I can say, for example, that in addition to the obvious things, the loss of Arctic seasonal sea ice, for example, we know that at 2 degrees warming, there are strong influences on food productivity. That is, there are many crops that are sensitive to temperature, and above a very limited range, further increases in temperature decrease the productivity of these crops. So there'll be, in addition, we get water stress, you know. And everything depends really on where you are and what you do. In San Diego, for example, 2 of the clearest effects are that we will suffer from sea level rise because it'll increase the likelihood of beach erosion of the North County cliffs, of saline water flowing into floodplains like Mission Valley. And also, we will suffer in Southern California from water stress because in the warmer world, there'll be less snow for snowpack in the Sierras, our natural reservoir, and the Colorado River is drying up too. So there'll be greater agricultural versus urban, you might say, competition for water, higher water rates, and a lot of dominoes flow from water stress, such as greater wildfire risk. There are a few parts of the world and a few industries that you can think might benefit from, say, a longer growing season. But in general, the bads far outweigh the goods. And some of the most sensible analysis that I've seen has been done by the US Department of Defense, which are not a bunch of ideological hotheads. They're very practical, down-to-earth people used to running billion-dollar operations, and they say that a warmer world is a world in which threats are multiplied. You know, the American farmer with high-tech agriculture may cope with changes in the weather in a way that the subsistence farmer in Chad cannot. And so you see a danger of failed and failing states, of environmental refugees, and so on. So there are a lot of dominoes that fall, and, but even at 2 degrees, and it will be, in my view, quite an amazing accomplishment if we're able to limit global warming to that, then there are deleterious effects, and they get worse the longer the problem is neglected.
Richard, thank you for an excellent talk. Thank you to the kids.
Thank you all.